Hello, today we're going to be doing an overview of the Opticline T3D system. So behind me we have a C614 T3D, and I suppose the main differences between the standard generation of Opticline and the T3D is we have a scanning tactile probe. So this is the SM25-2 that's supplied from Renishaw, and the principle behind that is that we've got scanning capability for features that we're unable to see using the optics to measure. So the setup here is an example of a probe that has a long Z negative stylus, but there's other probe setups that we can have on the system. Now we're going to take a look at measuring a hole diameter. So we're going to output the roundness as well as the diameter size. So on the top of the component here we've got a diameter, and I'm going to use a scanning probe to measure that feature. So we've got a program already written, so I'm just going to click the start button on the system. So the program, we found the length position at the bottom of the component. We've now found the rotational position, so we know where the hole is. And now we're going to bring the probe in to measure that roundness and diameter. And as you can see, within 17.3 seconds, we've completed the measurement. So now what we're going to do is I'm just going to delete the features, and we're just going to run through how I would program that. So within my program or to the drawing, I already know that this is the hole that controls the rotational axis. So all I'm going to do is go to my radial bore hole tactile data recording, and I'm going to click here. I know from the drawing that this is 202 millimeters away from my length reference. I know that the hole diameter is a 5 millimeter hole, and I'm going to use the end of my length 36 star probe. I would like to probe it at a 3 millimeter depth, and I want to use a ref as the rotational position for that feature. Now I'm going to go and get withdraw the values that I want. So first of all, I'll look at the roundness, and I just click the TO1 which you just created, and we'll call this roundness. I've applied a 0.05 tolerance to the roundness, and again we're going to do the same with the diameter. However, we've now got a plus or minus 50 microns. My nominal value for the diameter is 5. So now all I need to do is click start and watch that run through. So same principle again, we found the rotational position. Now we're bringing the probe in to come and measure that feature. And there we go. Now we're going to be taking a look at measuring keyways and slots. So on the front of our component here you can see there's a slot or a keyway, and what we're going to do is use the software to measure the depth as well as the width of that slot. So I've already written a program to do this, so I'm just going to click start. So same principle again, we've got the length position being found, our A-ref, our rotational position, and then we're going to find the rotational position of the slot. The first measurement we're taking is on the flanks or the sidewalls of the slot, so we take 4 points in each position as well as 2 points on the bottom of the slot for the depth. So you can see we've moved up to take our second level of points now. And then the last thing we have to do for the depth of the slot is to find the reference feature on the external. So we use the touch probe to come and take a point on the external diameter, and that gives us our width measurement. So now we're going to take a look at how we program this. So what I'm going to do is delete the features that we've measured, and we're just going to run through in the software how to program it. Okay, so I'll get rid of my radial point, I'll get rid of the scan data as well as the depth and the width. So I can leave it, this is just a generic rotational position, we're finding the valley, so this is where our slot is using the optics. So the first thing I'm going to do is go to my tactile area, and I'm going to go right to the bottom to find my radial position to start with. So I'm just going to take a point on the edge where the slot isn't. So I'll use the end of my L36 star, as well as using the rotational position of the slot position. So that's going to take the point for our depth. I'll now go to my favorites tab because I've placed the slotted keyway functions that we're going to look at into this area. So the first one being the data recording. I'm going to click here and click on the area where the slot is. I know from the drawing that this is 102 millimeters from my length reference position, I know that the slot is 12 millimeters tall, and I know that it's 4 millimeters wide, with an expected depth of 3 millimeters. I'm going to use the L63 star again. It's best to use the same probe, means we don't have to go and do a change tool, and I'm going to reference it to my slot position. The last thing I need to do is to scroll down to here and input my base circle diameter, and this is to help the system know how separate the points need to be for first the depth as well as the length positions themselves. So that has all the data now for me to be able to go and measure the width, so obtaining our Keyway tactile width, and I'll use my SK01. I'm just going to call that the width, as well as put in my nominal value of 4 millimeters with a 50 micron limit. I now need to find the depth, so I'm going to go back to my favorites tab, and I'm going to go to the depth, and I'm going to click SK01, and I'm going to refer that to my TO1, which is my radial tactile point. And the nominal value for this is 3 millimeters. However, the tolerance is 0.1 on this element, not 50 microns. So I'm just going to update those as well. And I'll change the naming convention of that to depth. And that is a run through on how we would measure the slot. So this is quite a key point to note. So the probe is currently running through a calibration. So within our INI file on the system, every 20 minutes we do a reference run to make sure the probe's still intact and it's measuring within an allowable limit. It's quite important. These machines are used for production environments. So if there was to be a drift or someone was to knock the probe, we shouldn't lose any more than 20 minutes worth of measured data. It's something that Genoptic have embedded into the systems. We do the same with the optics. So we can see now the slot is being measured. So we're taking our points on the left hand side, our depth point. Now we're going over to the right hand side, taking our 2 points, travelling up and doing the same thing on the top of the slot. Now the last measurement that we do once we've completed the internal slot measurement is to come and do our radial point for the depth. As you can see, the width is slightly out of spec, but the depth is in tolerance. So what I'm going to do now is just show you some of the other features that you can use the T3D to measure on a slot or Keyway feature. I'm not going to go into the detail of them, but if you've got any questions, then please let us know. So here is a list of the current slotted Keyway tactile measurements. So any questions, don't hesitate to ask. So now we're going to be taking a look at some profile measurement, as well as an overview on the differences between what we can do on a cam measurement as well. So within the machine we've got a component. I've got an external profile being measured. So the idea behind that is to show you if you had a blind feature or a blind profile that we couldn't see with the optics, that we could use the probe to measure that profile, as well as also taking a profile on the inside of the component. Obviously where we've got the Z negative probe on the machine, we're able to take internal measurements. So if we were looking at internal holes, radiuses, and that kind of feature. So all I'm going to do is click start on the machine, and it's going to run the measurement. So you can see the first measurement. This is the sort of more manufactured one as such. I'm just measuring the external chamfer length. I could do that with the optics in this scenario, but what we're going to do is just to show you the principle really. The next measurement, so within the Opticline, I'm not sure if I've touched on it yet, we've got a change rack, so we can house up to 3 probes, or 3 different types of probes. So we're swapping over to our star stylus now, and we're going to use the Z negative tool to measure the internal angle or chamfer. So that's now coming in now, and we can see it's going on the inside of the component, and it's measuring the profile. Okay, so as we have done before, what I'm going to do now is I'm just going to run through the principle of measuring an external feature. So if we were to look at the profile, so if we jump to the software, I'll just delete this feature here, and I'll delete this here, and I'll get rid of all of these as well. Okay, so on our T3D area, we've got our inside and our external or profile general tool using the T3D sensor. So I'm just going to click, and I'm going to go onto the area where my chamfer was. I'm going to select a 5mm tactile scanning length, as well as using the straight probe. I don't need a reference angle because this component's not got a rotational feature, and all I need to do then is click measure. So that is now going to bring the probe onto the component. It's going to come and scan the surface, and from that data we can then use it's almost a contour editor to be able to depict specific features that we need to output in the Solaris software. So just changing tools again, back from our star probe. Comes up now, comes in and takes the measurement. So you can see now when I go into the detailed contour section on the software, we've got our profile measurement. So what we can do is if I right click and go to update plan profile, I've now effectively got a contour set up. So I could go to my profile element straight line, draw an area, profile element straight line, draw an area, and lastly on the top surface, draw an area. Now we can create the intersection points. So between PR01, PR02, it's given me P4. I don't need to update the nominals for this specific feature, and also on PR02 and PR03, and that's now given me this element. If I now wanted to do the length position, I'd go to the length and I'd say PR04 to PR05, which is our created feature, and the nominal value for that I believe is 1.35, and we've got a 0.25 limit on that feature. So I'm going to update those. So now when I go back into my plan contour, you can see the features that we've created, P06 being our length with our nominal elements in, so I'm just going to call this chamfer length. And now when I click start, that's going to go and measure the external feature, and using the tactile probe, it's going to give me the chamfer length. So again, this is predominantly used for looking at features that the optics wouldn't be able to see in this scenario. So if we go into a standard cam form, which on the left hand side, again there's a bit more of a radius feature to the sample, but it gives you an understanding. If we were to look at an inverted flank, so we're starting to see more and more of our customers, especially when you're talking about F1 and you're talking about high sort of horsepower engines, what they're trying to do is to look at using an inverted flank because there's some form of efficiency gain to it. So the difficulty we have when we're using an Opticline system is that when you look at the light that is passing through to measure those features, on a standard cam we don't have any issue because we're not interrupting the light source to look at a negative feature. So if we were to zoom in onto the red or the circled area on the right hand side, you can see that we've got this sort of effective inverted radius. Now where the light is, we've almost got an area where we won't actually obtain any measurement. So this is the same when you're looking at a length position. If the surface is dished, we'll just see the worst case area. So now if we were to look, you can see that the optic wouldn't be able to see this area, and that's one of the main benefits to using the T3D for those kind of features. Okay. So it's a little bit of an overview and the types of profile measurements that we can make. We can do profile geometries looking against, say, a 0.1 limit. We can show the contour of that, which isn't a problem as well. So if you've got any questions on what I've just gone through, then please let us know. So now we're going to be taking a look at spline and gear measurement. So on the Opticline, using the scanning probe, we're able to measure against the contour to be able to look at pitch deviation and quite a few other features. So I'm going to click start on the machine, and I've got a pre-programmed routine measuring. So same again, we're finding the rotational position, and then we're bringing the scanning probe in to be able to measure the feature. So one of the key differences to the Opticline system in comparison to other shaft scanning systems that may have a probe is that we've actually got the Y and the X-axis movement. Obviously with the optics we've got the Z. But it enables us to have a better contact point on some features, especially like a gear. The SM25 probes are designed to not have too much pressure in this orientation, the Y positive direction. The sensor is meant to be deflected in the other way, which is why it's quite beneficial for looking at these kind of features. So as you can see in the software, the total pitch error is 0.06 and the pitch deviation individually is 0.025. So if I just flag up some of the other features that we could measure using the tactile probe. So these currently are the features, and I know the gear specialists that will be watching this, the acronyms here are what you're probably more interested in. Genoptic are spending a lot of time at the minute in the software development, so I expect there to be more capability coming, and if anyone's got any queries on the future outputs that are going to be there, just let me know and I'll be able to forward that on to you. So what we'll do is we're going to, same again, just delete the features that we've previously measured, and we're just going to go through and remeasure and show you how we do it. So I'll go to my tactile, I'll scroll down, well actually in my data recording tactile I've got my outside toothing. One key thing to note is you've probably noticed we've got the star styli available, so we would be able to do an internal gear as well. So if you had a gear or a spline on the top, we would be able to access that with the different setups of probes. So if I go to my outside toothing and we roll in, I'm just going to take my measurement here. So it asked me what the probe element I'd like, so I'm going to bring the probe to the front so we can see it. So I'm just going to use this, the second probe here. I'm then going to go to number of teeth, and on this gear we've got 30. I've got a module of 1.1 and my nominal pressure anger is 20. And from there my measurement is effectively ready to go. So what I'm going to do is just go into the gear measurement area and just select some of the parameters that we've previously measured. So the first one we'll look at is the pitch deviation, and you'll see that we get the data recording. All I'm going to do is select my TO1 and it inputs the values for me. If I same again, I'll go to my total deviation, so scroll down, I've got the adjacent pitch deviation, we'll select that one. We go to TO2, and that's an example of effectively we have our data recording and then we're selecting the features that will be output from there. So as a program, I've effectively created a measurement, and all I need to do is click start. And as you'll see again, the rotational position and LREF will be found, and then the scanning probe will come in and measure that feature. And there we have it. So thanks very much for watching.